Hi, hello. Welcome to my video for the geotechnical software. And today I'm going to talk about how to undertake analysis for single piles subject to lateral loading with using PY curves. The program we're going to use today is a finite element based program which is called PileLAT. I think you can see from my screen that this is a quite typical interface for the PileLAT program. The example we're going to use today is a very simple one. There are two soil layers. The pile length is 25 meters long. There are loadings applied at the top of the pile head. And also, there is a cantilever length of about 5 meters above the existing ground surface. Regarding the groundwater, we assume that the groundwater table is at the ground surface. So now let me show you how to define the various inputs for this problem. We can start from the pile section parameters, soil parameters, and how to define the soil layers, how to define the loadings at the pile top, and also how to carry out analysis and how to view the analysis results. So let me start a new analysis file. So you can see we can start a new analysis by clicking this button at the toolbar here. This is called a new file. Let's click this one. Then we'll be asked whether you want to save the changes or not. So for this case, of course, we say no. We're not going to save any changes. Then this will bring us back to the beginning of this program. This is the dialog of the new model initialization. From this dialog, you will be asked, actually you have two different choices. You can either start a new project or you can open an existing project. So for our case here, we just click the first button. We say, let's start a new project. Once you start a new project in PileLAT program, it will give you a default analysis input file. Within this default input file, it will have one single soil layer and also the pile length and also some default loading on the top of the piles and also the groundwater table. So actually we can modify this one to create our own analysis input file. So now let me show you how to do this. So you see here, we already open this default input file here. Then what we're going to do is that we need to define or we need to update the analysis option. So let me show you how to do this one. On this top button here, there's quite a few buttons here from the toolbar, which we call it the top toolbar. This is the second layer of toolbar. So this one is called analysis option dialog. Just click this one. This dialog will be invoked. From this dialog, you can select a few different options which you may need for the power analysis. For example, for first one is that analysis option. Currently there are two options available in PileLAT. The first option is use soil layers input by users, which means that the user can manually input the different soil layers and also soil parameters for the PY curves and use those input for their own analysis. This is the first option. The second option is that use CPT file imported by users. If this option is selected, the user is able to import CPT record into the program, and all the analysis will be carried out based on that CPT profile, which means that for the soil strains, whether it's engine shear strains for the clay or effective friction angle for the sand, all those parameters will not be required anymore, and the power lateral force analysis will be based on the CPT record, which is QC values. However, for this case, for this video, we'll just use the first one, which is also a conventional way to carry out power lateral force analysis with PY curves, nonlinear PY curves, by the way. The second one is a mesh option. Because this is a finite element based program, actually the analysis is based on the meshes created by the program itself. So we have two ways to create a mesh. One way is that we can let the program automatically generate a mesh just based on the layer thickness. Or we can also manually input of the mesh element numbers, which means that if we, for the second option, we can just directly input the number of elements into the program, and the program will calculate the node point just based on the mesh numbers. So all the nodes will be evenly spaced. And of course, if you want to change the position of some nodes, you also can click this button, which is Add Pi Node Position. So in this dialog, you can change the node position and add different depths. As you can see currently from the screen now, that actually the distance between any two nodes actually are the same, which means that the mesh is quite even. So let's close this one. And also you can just, maybe you don't need to input the number of mesh by yourself. You can just let the program automatically create it. So once this option is selected, you have 5 different degree of fineness for the mesh, from very coarse to coarse, the medium, fine, very fine, and for each selection, it will correspond to a different mesh number. For example, for the very coarse mesh, you can see here for the mesh information here, you can see number of power element is 33. And if we click coarse, it will increase to 50. If we select a very fine, which is finest mesh we have, which is 133 here. I will just show you how to visualize this one a little bit. For example, if we just choose very coarse mesh, and if we click OK, actually you really didn't see anything different on the screen. But if you click here, display setting, if we show the power mesh here, click OK, you can see all those node points here. Yeah, this is actually this corresponds to the very coarse mesh. So if we change to just say fine mesh, click OK, you can see that we have more node points here, which means the mesh is finer. So if you don't want to see those node points, sometimes it's just too much. You can just switch off this one option, untick it, Pi mesh, then click OK button, so it will come back. So for for this case here, oops, we will just use maybe medium mesh. Is okay. Let's clear this one. So this is a mesh. After update this analysis option, sometimes you don't need it because those are all very standard inputs. Actually, you really don't need to change it. So that's fine. Yeah, no problem. So after this one, so next step is just to define the power section we want to use in the analysis. So this button is called define power section. Let's click this one. This dialog will appear. From this dialog, actually we can define the section type we want for the power. So the program provides about 7 section types, from circular section, this one, or rectangular one, which require the section properties of width and height, and also for this one, and for this one it only needs one parameter which is called diameter. This is the octagonal section is a quite common one for the pre-stressed driven powers used during the bridge works. You also can have this steer hedge section. Strong means that actually the loading direction is towards the strong axis direction, which means bending stiffness is high in this direction. And also you have this hedge section weak. This is the loading direction is towards the weak axis direction of this one. You have this pipe section, and also the last one is user defined section. Actually, on this section, actually user can define what is the width of this section, what is the moment of inertia, what is the section area, what is the section parameters. The last two actually are mainly for the power vertical capacity analysis, which we will talk about in a different video. For the power lateral force analysis, moment, this one, moment inertial, I, is the most important parameters. And of course, this width B is also important because this is a parameter will be used to calculate the soil reaction. So for the material properties on this one, and we can import this Young's modulus for the power material. For the power material, it could be either steel or concrete. For the concrete is about 30 to 40 GPI. For the steel, could be something around 200 GPI. This last option is called display settings here. Actually, it has nothing to do with the calculation itself. It's mainly used to for the displaying purpose. This is the line thickness. For example, current is 3. If we increase to 4, you can see if I click apply, click OK, you can see that actually on the screen here, actually this line is thicker. Actually, this line represents the pi within the ground. And of course, the color also can be changed. If we select a different color, for example, if we select orange, you see that will be changed. But I don't like this orange color, so let me change back to this blue one. Another very important parameters for when you define power section is called section length. Actually, is the length of this section. Actually, for the powers. So for example, if we only have one section, so the section length is 25 meter. So this means that the power length is 25 meter. But if we have two sections, for example, just under this tab here, this is section 1 because currently we only define the default section is section 1. which is only one section. Actually, we can add another more sections if we need. For example, I add another one, click add. This is section 2. Let's say maybe I want to have rectangular section for this one, but I don't need 25 meter long. I just 5 meter long. Keep the rest the same. This is the same. Use maybe a larger line thickness just for displaying purpose. Select color is image. I select purple. Click OK. I click OK. So you can see that actually I have another here. This is another power section. Of course, here is that because our layer thickness is only 30, so it's really at the bottom of layer thickness. For better displaying purpose, let me change the layer thickness just to 40. Yeah, then it's slightly better. So maybe let me change to 8. Thickness is 8. So you can see that. So the first section is 25 meter, and the second section is 5 meter. So total is 30 meters. Actually, the total power length is 30 meters. So we can add more sections if we want, and for the problem we have. But for this case here, we just use one section. So let's delete this one. Let's delete it. So it's only 25 meter. Let's go back to circular section. 0. Let's say 1.0 meter for the diameter. So this is OK. 35 GPA. Let's say click OK. Yep. So we define the power section parameters, section type, and also the section length. Because we only have one section, so which means that the total power length is only 25 meter. So after defining the power section and the power length, so we can start defining the soil layer and soil parameters. So let's define the soil material with PY curves first. Let's click this button. So by default, there are 2 different materials already within this PY curve material sets. The first one is called null material. This material is used to represent the void or any cantilever length which will not offer any soil resistance to the pulse. Basically, it's nothing. It's null material. It could be water, it could be air, it could be nothing there. The second one is API soft clay. So if we double click this one, and then you can see that there's another window with detailed inputs of the various soil parameters for the corresponding PY curves. So here is that we have a PY curve model. This is a drop-down menu. When you click it, those are all the PY curve options you can select from this program. First one is non-material, followed by the API clay. Then this is API clay RP2GO. This is the lightest API clay PY curve model. Then you have Matlock soft clay, stiff clay without water, modified stiff clay without water, stiff clay with water, elastic plastic clay, C5 soil. So up to here, then those are all 4 cohesive soils. Then starting from this point on downwards, you have API sand and also sand by Reese, then liquefied sand, then elastic plastic sand. Then you also have this calcareous soil, 2 different models, which you can use input CBT data, or you can just manually put the QC values into the program as well. We will show you later on. Then you have this lock, weak lock, Reese, strong lock, massive lock and a weak calcareous lock, also weak carbonated lock by ABBS in 1983, and elastic plastic lock. Those are all nonlinear PI curves. You also can have this elastic subglide, which means you can just put an elastic spring into this one. And of course, the last one is that you can use user-defined PI curves. We will talk about this one later on, maybe in a different video because due to the time limit. So for here is that for this API client, this one is the general property is a total unit weight. This is the basic soil parameters, which is, you can see here, there are two parameters here. First one is unjoined shear strength. Second one is rate of change for unjoined shear strength. So here put 0 for rate of change, which means that within this layer, the unjoined shear strength is the same value. So at the top of this layer, the unjoined shear strength is 30 kilopascal. So this one here, you can see that this is for advanced properties for API client. There are two main parameters are required for API client. One is the EPS 50 factor. Another one is a J factor. For the EPS 50 factor, its value is based on the value of unjoined shear strength. So if we click this button here, it will give you some simple guidelines how to select this value. You can see here, this is title of this dialog is typical value for strength factor, EPS 50. There are a different range of unjoined shear strengths. This is a recommended strength factor value. So PileLAT user can just based on whatever they select here, for example, 30 kilopascal. So he can select this one. So let's select this one, which is 0.01. Let's click OK. You see, this one becomes 0.01. For J factor, actually the same thing. This parameter also depends on the values of unjoined shear strength. So our is 30, so it's less than 48 kilopascal. So let's select this one, 0.5. Let's click OK. So it's OK. Oh, I just forgot to mention that we also can change the material name. And for example, in this case, I just changed material name to soft clay. Yeah, you can see here, once I click the enter button here, or either I press this apply button here, the name is changed. And also from this list here, the name is also changed. Let's click OK. So we also need to define another one, which is Lucent. So let's click this button new. The default name for the new material is called new material 3. Let's double click this one, or we can click this button. Click this button. So this is material name, new material 3. The default PI curve mode for any new material in PileLAT is null material. Yeah. So let's click this drop-down menu. Let's select API send. So let's input the unit weight. Just say 18. Friction angle 30. And this is a subgrade modulus, KS, for the APSN, which we need to provide. So we can click this button to get some guideline. Because our file is 30, so according to API standard, data menu, we can just say select this value. This is about 11 meganewton per meter cube. Let's select OK. And of course, if you have any monitoring data or back analysis results, you can put it here, and a different one is OK. Yeah, for this case here, we just use this default one. We just click OK. Then number is here. And also we change the name to Lucent. Click button. You can see that it's changed. Let's click OK. So we can see that the color of this one is a green color. If we want to change the color, we can just click this button, color button. For example, we want to use this color, but it could be too dark. Let me go a little bit lighter. Say OK. Yes, you see the color changed. Let's click OK. OK. So we already defined the soil materials with PY curve parameters. So, but this geometry here actually still remains the same. And this because we haven't defined the soil layers yet. So let's go to next step. Let's define the soil layer. So this is a button next to this soil material defining button. Let's go to this one. This button is to define soil layers. Let's click this one. You can see that from the current dialog, there's only one soil layers. So for our case, we need to consider three different soil layers. First one is a non-material, which represents the cantilever portion of the piles. Then second one is soft clay. Third one is loose sand. So let's say add three. Okay, there's three different material. So first one is non-material, but it's not 40 meter thickness. It's only 5. Let's say 5. You see all change here. So the second one is soft clay model. The material is soft clay. It's okay, but its thickness, let's change to 15. You see, once I change here, and actually this main interface actually is also changed. Then last one is loose sand. I want to also use 15. You see, or changed. For the groundwater table, by default, the groundwater table is always at the top of the geometry, which is at the top of the first soil layer. So for this case, that's why our groundwater table is at the existing ground surface, which is at the top of the second soil layer. So we can change here. So depth of water below the ground surface, let's change to 5. Here the ground surface actually means that the top of the first soil layer, which is currently, for this case, is a non-material. So let's click OK. Then you can see that actually we already defined the soil layers with different thickness, and also define the power length and with the section parameters, and we defined the water table. And you also can see from here that for each soil layer on the main geometry here, you can see some critical parameters, for example, name, strength, total unit weight, and also the name of the PY curve model. So for the next step is that we need to define the loadings here. Now let's start creating some loadings on the top of the piles. Please note that there are already some default loadings on the top of pile from the default input file. So we need to make change to those loadings just to suit our needs. So what we can do is that just under this button here, this is the second toolbar. This is called, this button actually is used to define the pile head load. Let's click this one. Then this dialog will appear. This is a table. This number means number of the, actually we can define multiple sets of the loads at the top of the pile. In this case, for our program here in this video, we only consider one set of loading. So this number is 1. Of course, if we need, we can add more. For example, we can add more. Yeah. Then let's delete this one because we're going to use 1. The second column is called pile head boundary conditions. There are 5 different pile head boundary conditions we can use in PileLAT program. First one is a free power head. The second one is a rigid power head, so there's no rotation. Third one is a partially restrained power head, so there's a rotational spring will be applied at the top of the power. The fourth one is a specified deflection and moment. So either we can input a specified deflection, for example, 20 millimeter or 30 millimeter, just at the power head, and also we can apply a moment. Last one is a specified deflection and rotation, so we can input a specified deflection value and also rotation value at the top of the power. In this case, we just use the first one, free power head, which means that the power head is free to move and also free to rotate. So we're going to use for this column here, the first column for the load is called the actual load, which is a vertical force. So we just say we use 500 because we use this load. So if we need to consider any P delta effect for the pulse on the lateral loading, so we need to use this actual load. And of course, if we don't have any actual load, we can just put 0. For this case, we just put 500. Then shear force we also put 500. So notice that the direction is that from left to right, that is a positive direction. So it's 500. So you can see that when I put all those loads here, actually those numbers will be updated from the main screen here. I also want to put some moment. Let's put a 50 kilonewton meter. So you can see here, this moment appears here, 50 kilonewton. Let's click OK. So this load cycle is that if this is cyclic loading, we can put maybe 100, 200, 1000. But if the number is 1, which means that this is static loading. So in this case, we only consider static loads. So let's say OK. Then you can see here we already defined loads on the top of the piles. So what's next is that I think we already defined everything we need for the analysis. We defined the soil layers, defined the power sections, power lengths, soil parameters, water tables, and also loads at the top of the piles, and also the mesh. And remember, as I mentioned before, if you want to see the mesh, you always can switch on this one. So you can see the mesh here. And also, if you want, you can see the soil spring here. Yeah, which is a soil spring, actually imaginary soil spring attached to every node, yeah, which is the basis of the PI curve model. Because for every spring, actually is a nonlinear PI curve. So if you don't want to see this one, so you can just switch it off. There's many options here. Actually, you can switch on, switch off. For example, for the water table, you can switch off if you don't want to see it. Yeah, and switch on if you want to see it. That's fine. So now it's done. So we already completed our inputs preparation for this case here. So let's go to the next stage. Let's go to run the analysis. So in order to run the analysis is that we just need to, it's very simple. We just need to click this run button, or under this menu, we just click this run analysis item here. So let's do this one. Let's click this run button. Usually analysis is very quick for the power lateral force analysis with nonlinear springs. So it says that the load case 1, remember we only have one load case, so it's a load case 1. And if we have multiple load cases, you will see more lines here, load case 2, load case 3. Then it says that all analyses are successful. Open the output window to view the results. Let's click OK. From this, at this stage, you will notice that actually some toolbar buttons, or most of them actually are grayed out. This is because those buttons actually are only required during the input stage. Once we finish the analysis and the analysis is successful, so we don't need them anymore. And this, so all the inputs will be locked, which means that we cannot change the input anymore. If we want to change the input, so we will have to click this button. This is called the lock and unlock button. We have to unlock this analysis file, which will delete all the analysis results. So which means that if you want to keep the analysis results, so you really don't want to do any changes to the input files, that's fine. Let's keep as it is. But if you want to change something, just like change some parameters, change loading, you may need to click this button, unlock. You may need to update your input file and run again. Actually, this actually is used to prevent the user from changing any inputs once their analysis is finished. So in order to view the analysis results, we just need to click this button. This is called View Analysis Results. This is the only button we need to click. Then we have this new window here. This is output window. From this window, and you can view different analysis results, such as this is the main screen, main graphic output of the analysis results. This deflection, bending moment, shear force. This is the load case. Because we only have one load case, so this is only one here. This is a summary table for the power section parameters. Because we only have one section, so there's only one column here. This is a table just below this main graphic area. Actually, this table shows the detailed analysis results at each node point along the pi, such as deflection, rotation, bending moment, shear force, reaction, and also PU. PU is ultimate large soil lateral resistance. Ks is this spring stiffness. EI is a bending stiffness. Sigma V is a total vertical soil pressure. This is sigma V prime is effective soil pressure, which is actually is a vertical stress, effective vertical stress. Sigma W is a water pressure. Those are all the data here, and just along the power length. So actually, this provide a very detailed presentation of the analysis results. So we also can select different results for the plotting purpose. For example, let's right-click mouse. There's a floating menu here, and actually for the second one view, for example, we can change the middle graph just to change it to soil reaction, soil spring reaction. You see here, actually we changed it. For example, for the first one, we just move to the mouse to the figure where you want to change the results. So let's right click here, view. Let's say I want to see the lateral, ultimate lateral resistance PU. So it will show you the results here. And for the last one, for example, I want to change to the deflection. It will change here. And we also can change the, for example, change the plotting style. Let's select this one, plot style selection. For example, line color. For example, if I want to have, for some reason, I want to use this color, it will be changed. If I want to use different line thickness, it will be changed. If I want to use, for example, from solid line dash line, if it will be changed. So all this will give you very different options just to for the presentation purpose. Apart from this main graphic plots here, you also can open the single plot. For example, for those items here, first item is that first main item is that called the power results for the selected load case, which means that for the load case here, if we just let us double click this one, burning moment, it will show this results just for this load case. This is a separate dialog. So with slightly different presentation. So on the left-hand side, it will show the profile of the bending moment. And on this one here, it has a table, which will give you very detailed breakdown regarding the bending moment forces here, just at different depths. And also, as you can see, that actually the soil layer are also superimposed here. And so you can see that at different depths, and for example, at this point here, it's within this soft clay, and within depth here, actually it's within this low sand. Then just similar to this main graphic area, the color also can be changed if you want. For example, if we change to this color, it will be changed. So let's say OK. Let's click OK just to close this one. So far we talked about the main analysis results, such as deflection, bending moment, shear force, soil reaction, yeah, something like that. Actually, we also can see the PY curves at all node points along the path. Let me show you how to do this. On this toolbar here, it's called the PY curve plot. Let's click this one. It will open another dialog, which is called PY curve output. So it will list down all these node points, depth, level, and also the material type. From the first one to the last one, you can see that API clay, API sand. So for example, if I choose any numbers, for example, if I select this one, select this one, select this one, I can say click this button, plot. You will see that this is PY curve plots for the selected nodes. And of course, we also can just say select all, and it will automatically select all the points. And we click plots, and you can see there are so many curves here, but sometimes it's just too much. Let's just click on select, and we just select what we really need to see. Maybe a few, yeah, location, a few, maybe shallow, deep location, and also for the points within the sand, let's say plots. Here you can see this is vertical axis is the power lateral resistance in kilonewton per meter. The horizontal axis is displacement in millimeter. So if we want, we also can see, just right click on this graph to invoke this floating menu, and you will see that there are two items here. One is copy. If we press copy, so this figure will be copied into the clipboard. Then you can paste it into Word file or spreadsheet for reporting purpose. And of course, you also can click the second one, table. Once you click this one, you will see that on this table, it will tabulate the detailed PY curve results at every node. The user can select node. For example, we can select a certain node. For example, we select node at 6.5 meter depth. This is node number 18. You can see that this Y is the displacement in millimeter. This PU is power lateral resistance in kilonewton per meter. This is a line load. So this is nonlinear PY curve at this point for node number 18 at 6.5 meter below the ground surface. So let's close this dialog. So this is for PI curve. So actually we can have lots of information regarding the PI curves at every node along the path within the soil. So as you can notice here, if I just move my cursor here, at the bottom of this dialog figure, you can see that actually this is called point coordinates on PI curves. So it's a real-time displaying of the x and y coordinates on the PI curves. So the user can just have a feeling regarding the values of the PI curve. Yeah. So that's it for this PI curve output, which could be very valuable. And for example, if the engineers want to know a little bit more into the details of the PI curves at certain depths, it could be quite useful. So let's code this one. And also, we also can get the equivalent stiffness at power head from the analysis results. Let me show you what is this one. Let's click this one. It will invoke another dialog, which is called equivalent power head stiffness, deflection, and rotation. So this fig will give you a plot for the power head stiffness for various components. That could be either sediment in the vertical direction, or just for the deflection, or for the rotation, and for the bending. For example, for K32 is power head bending moment versus deflection. K33 is a head bending moment over rotation versus rotation. Those are the typical power head stiffness. So you can see here, this is, for example, K11. You can see this K11 stiffness relationship between this one and the settlement. If we click this K22, which is the power head shear force and deflection, this is the one. You also can see the rotation, also can see the bending moment and the rotation, and this figure is here. And on the right-hand side of the dialog, you can see the detailed numbers for this figure. So which is also quite useful. And so usually we use this information and to do the structure design. We carry out this power lateral force analysis in the geotechnical software. Then we get the power head stiffness matrix. Then we import into the structural software just to do the structure analysis. So the last one is this I want to show you is called the low settlement curve. So remember that we also input the vertical force on the top of the pie. So for this vertical force, actually program can calculate the power settlement under this force. So actually this one give you a trend, give you a relationship between the actual force at the power head and the settlement. Actually, this calculation is based on the Fleming's approach, which is a paper published in 1992 in Geotechnique. We may have a different session to talk about this one, to give a little bit more details regarding how we can carry out this power settlement analysis. So the last one I want to show you is that report generation. So if we click this button, so the program will automatically create a simple report with all the critical data. So the user can actually save this one into the Word file or into the PDF file and for the reporting purpose. So For this output report, it has very basic input information such as soil layers, PI curve parameters, surcharge loading. This one we haven't talked about in this video. We may talk about this one in a different session. How to consider surcharge loading at the top of the soil layer. And also you can see here number 4 is soil layer inputs for the power settlement analysis. This one we also didn't touch it in this video, so we will talk about it in a separate video. This is the power section inputs, the length, section type, basic section parameters. Remember, we just use circular section. Power diameter is 1 meter, and this is typical Young's model for the concrete. And the bending stiffness option is elastic bending stiffness, and this is the option we used in this session. Actually, there are also quite a few different options which can be considered for the power bending stiffness. We will discuss that one in different videos. This one is horizontal struts and the rotation spring. We haven't input any of those into this case, so it's all 0. So this is the analysis option we talked about in the beginning of the analysis, all here. And then section 8 will give you a very detailed breakdown regarding the analysis results, basically depth, displacement, rotation, bending moment, shear force, and also the soil reaction. PU is the ultimate lateral resistance, soil spring, and bending stiffness. And also there's a very nice summary regarding the minimum and maximum numbers. For example, minimum deflection, maximum deflection, minimum bending moment, maximum bending moment. This could be quite critical information for the analysis. So okay, so I think this concludes this video, and we try to capture all the important items in this video, but still there are still quite a few we haven't touched due to the limited time. So for those ones, I will make some other videos just to give the user a little bit more explanation. Thank you very much. Thanks for watching.